Hello, I'm Sue Nelson and welcome to the Planet Earth podcast. This week we're in North Cornwall on the coast where science and sea collides for a project that will save lives. Also on today's podcast, where to trap carbon dioxide for millions of years.
Got some in the bag here. This is a sample of some Sherwood sandstone. As you can see, it's quite grainy, it's red in colour.
And more on that story later. Cornwall is one of Britain's most popular tourist destinations, especially during the summer, not least because it has some wonderful beaches, and I'm on the sands of one of them, barefoot at Perranporth. Unfortunately though, each year on many coastal resorts there'll be a tragic accident where someone underestimates the power of the waves and is pulled out to sea. Rip currents are a particular hazard and they're considered one of the most dangerous natural phenomena. As a result, rip currents have become the subject of joint research between the University of Plymouth and the Royal National Lifeboats Institution. And joining me on Perranporth Beach on quite a blustery day, huge waves in the distance there on the sea, is oceanographer and twice former European surfing champion Paul Russell, from the Centre for Research in Coastal Science and Engineering at the University of Plymouth, Tim Scott, also from the university, and lifeguard Dickon Berryman from the RNLI. Dickon, perhaps we could begin by explaining what a rip current actually is.
Put simply, a rip current is a body of water trying to find its own level. So stood here at Perranporth at low tide, we have got a good maybe 4 or 5 foot surf breaking, quite a big surf, lots and lots of water forcing its way onto the beach. Now that water's got to get back out again, so it will look for the path of least resistance. So on a beach like Perranporth, it will be a break in the sandbanks where there's a dip slightly deeper, and that water will flow out through it. On a different beach, it might be a pier or a jetty or some rocks, and there'll be a path that will follow the edge of those man-made or physical hazards, and just sluice back out to sea. So it's a natural cycle of water getting back to where it should be.
And what sort of problems do these rip currents cause for you as a lifeguard?
They account for at least 2/3 of our rescues, so a lot. We're always looking for a safe area to put our swimming flags away from the rip currents, and we'll always be advising people to avoid them and come up and swim between the red and yellow flags.
And it's not just a local phenomena, is it? It's not specific to this particular area.
No, not at all. I mean, around the world, they're prolific around the world. Wherever there's waves breaking, wherever there's lots of water movement, that water will eventually obviously need to go back out to sea, so there will always be rip currents.
Paul Russell, tell me a little bit about this particular project that you're doing.
Okay, it's a 3-year project, and we're looking at the factors that cause rip currents to vary, and we're measuring those factors. The factors are the incoming waves, which drive the whole system, measuring the rip currents themselves using the drifters, and the shape of the beach, the sandbanks and the rip channels in the beach and how those change. The crucial thing about the UK is that we have these large tidal ranges, so the water's moving on and off the sandbanks quickly and the waves are changing quickly, and therefore rip currents can turn on and off very quickly, and this is what causes a major hazard.
Now, you mentioned the drifters there, so this is part of the equipment that you're using to measure this. Tim Scott, you were involved in designing this equipment. Probably best to start, as it's already been mentioned, with the drifter. What's a drifter?
Well, the drifters themselves stand about a metre tall. The base of them is made up of a cylinder which is about the size of a 2-litre drinks bottle, and above that is a mast which extends up to about sort of waist high. The drifters themselves float, they're kind of neutrally buoyant, so when we put them in the surf zone, they float with the mast sticking upright and standing up. They have a damping plate on the bottom which stops them from surfing on the waves, and they very effectively mimic what would happen to a person if they were trapped in the surf zone and they were moving around on the rip currents.
How many would you use?
Well, we use about between 15 and 25. Each drifter itself has got a GPS unit that tracks its location, and it takes a position every second. We use a couple of interesting survey techniques where we can use a GPS base station to make these measurements much more accurate. These enable us to get very accurate velocities and positions within the surf zone using these bits of equipment.
Paul, we've got a sort of taste of some of the parameters that are being measured there. What else are these drifters, these GPS tracking devices actually looking for in the water?
Because we continually reseed the drifters, so they either get taken out to sea in a rip current or they get washed it back in by the wave. So we're continually reseeding them. So what we're looking for is the changes in the system. So not just measuring it once, but continually changing it as the tide changes, as the waves change, and as the seabed topography, the sandbars change. And we've just done a 6-week experiment here, which encapsulated quite a range of conditions, and we're coming back in October when the beach will be different and the waves will be different and the rip currents will be different, and we'll be repeating all the measurements then.
Now, both Tim, yourself and Paul, both keen surfers, have you noticed just purely with your surfing, because there are people here bodyboarding, taking surfboards out, obviously to enjoy the waves, have you ever noticed yourself that there are certain times of the year or the day when the rip currents seem to be stronger than usual?
Yeah, well, as a surfer, you spend a huge amount of time in the sea, and you see rip currents all the time, and you're constantly in rip currents and moving around. And many surfers might not know exactly the physics behind what's happening, but they're certainly observing them all the time, and they have a really good intuitive knowledge of how these rip currents work. And the fact is they do change all the time, and from seconds, from groups of waves, all the way through to seasons, and annually you get different kind of rips on different kinds of beaches.
We've also got fixed instruments out here measuring the current at one point, but the drifters will follow, just like a surfer, they'll follow where the currents are taking them. So in big waves like this, you get washed along the shore a bit, and then you get taken out in a rip current. Then a surfer would be riding waves, which would be the water being dragged back in over the bar, and then you're washed along shore again. And this is exactly the sort of circulation that our drifters do when they're out in the waves.
So, Dickon, this research that's interesting, really, it being done between the RNLI and the University of Plymouth, you're going to use this to help advice with lifeguards such as yourself, not just here, but equally applicable across the globe.
Oh, without doubt. I mean, it's at least threefold. We've got the initial risk assessing, the dreaded risk assessing that we all have to do, and that for us really determines, how many lifeguards we have, how much equipment we have, what sort of level of training we need on every beach in the UK. And what these guys are doing is feeding into that and giving us a base sort of data. So, this beach is so dangerous, and it sits on a scale, and that will feed in with all the experience and the observations and everything else to determine what we need. It also feed into our safety advice. So we do lots of schools education, we do lots of active education on the beach, and like I said, with preventative actions, we need to make sure we're giving the right advice, and it might change that, it might tweak that somehow. And also into our training that we actually give our lifeguards, these are young men and women who potentially grown up in the surf. It's backing up the knowledge they've got, but it's also how they maybe observe the surf and look for these rip currents and feed into how they do their job. So it's a really, really useful bit of research. And of course, if it's related to here, it'll be related to around the world. Wherever there's rip currents, this will be relevant.
Have you ever been tempted, Paul, as a former surfing champion, to get in there amongst the drifters yourself and see how it actually goes?
Oh, absolutely. I've just spent the last 5 weeks drifting myself with the drifters. It's incredibly hard work. They circulate around, continually get washed in. We're continually taking them back out. And we've been human drifting with GPSs on our heads to make sure that we track similar directions and at similar speeds to the drifters, which we do. But it means that there's been a whole groups of us being swept out in rip currents and being picked up, really following the drifters around.
Well, good luck with the next 6-week research project here. Tim Scott, Paul Russell and Dickon Berryman, thank you all very much indeed. You're listening to the Planet Earth podcast from Perranporth Beach in North Cornwall. Carbon capture and storage is being seen by the government as an important way of reducing emissions of carbon dioxide into the atmosphere. The idea is that the carbon is captured from power stations or factories and then piped deep underground and stored in rock forever. The theory's good, but how do scientists know that the carbon is going to remain trapped and not leak out? Richard Hollingham has been to the British Geological Survey at Keyworth near Nottingham to meet scientists studying the process of carbon capture and storage. He began by talking to experimental geochemist Keith Bateman.
First of all, you've got your carbon dioxide gas, which is then compressed, so it's easier to pump along a pipeline the same way as you would do with gas or oil. You then, in the reverse of the extraction process of gas and oil, you pump it down a well into a suitable geological formation where the carbon dioxide will then initially start to dissolve in any water that's there, and over time chemical reactions will occur such that the carbon dioxide will then react with the host rocks and produce new carbon-bearing minerals which will permanently lock the carbon dioxide up.
Caroline Graham, you're studying the seal at the top of these areas where you're looking to inject carbon dioxide. Give me a sense of what you're doing, because you have this enormous cabinet in the centre of your laboratory with a big red triangle on the front and a lot of tubes and wires I can see through the glass-fronted doors.
The big box is an oven which is designed to simulate the temperatures that the rocks would experience deep within the earth, and the tubes allow us to inject fluid into a sample of rock so we can look at how the flow processes will change with time.
So let's have a look inside the process going on. So open that. Whoa, the heat really hits you, doesn't it, as you open that up? And it looks like a big saucepan or pressure cooker in the centre.
It is, yeah. So we are pressurising the material. We will put it in a jacket to keep it secure from whatever we're squeezing it with, but we're squeezing it with a liquid around its outsides, and that simulates how the rock would be squeezed in the earth. These two vessels on either side of it are used to contain the gas or the liquid CO2, which we then inject from these vessels into the big pressure cooker.
So this pressure cooker is a simulation, really, a model, if you like, of what's going on underground when you inject carbon dioxide.
Yeah, exactly. So it's being squeezed, it's being cooked, and while that's happening, we're also adding in the carbon dioxide and seeing how easily the carbon dioxide will flow through the seal material. So what's the upper limit beyond which we can't pressurise the reservoir any further, at which point the seal may become compromised. So we know how secure it could be.
Well, Keith, we've come through into the next laboratory, which is an awful lot colder. Let's just get a sense then of what is going on underground when you inject carbon dioxide. What's there? There's a cap, and then there's, a reservoir?
A reservoir rock. Yes, I mean, what you'd use typically as a reservoir rock is a sandstone. Sandstones are naturally porous, and it's the same sort of rock that you will already find the natural gas that we use and the oil that we extract. And
so you've got some in a bag here.
Got some in the bag here. This is a sample of some Sherwood sandstone. As you can see, it's quite grainy, it's red in colour. You will see this all over the North Sea, and in fact we're quite lucky that the North Sea is a great area for storing carbon dioxide underground.
And it's evidently sandstone because a whole lot has
Yes.
gone on the floor.
You can see it going off of my hands.
So you've got a cap, so it's not going to escape. But the other point here is that the carbon dioxide is not in there as gas. It will change over time, or the rock will change over time.
Yeah, so over time, when you inject your carbon dioxide, it'll go in as a gas, or particularly a compressed gas. Over time, that gas will first of all dissolve in any water that is present. Typically that water will actually be quite salty, saline, stronger than seawater. As the carbon dioxide dissolves in that fluid, it would actually make the fluid more dense, which will over time will allow the carbon dioxide to dissolve and reach out further and further into your reservoir.
Which is the point to bring in Chris Rochelle here. You can demonstrate this, can't you? This flow through.
We can show this process in the lab with very simple lab experiments where we fill a tall, thin cell, a bit like a piece of double glazing, but thinner. We have a solution in that which is coloured. We put CO2 on over the top of it, and as this carbon dioxide dissolves, it changes the colour in the solution, and we can see fingers of carbon dioxide rich water dropping down over time slowly through this solution. And we can compare this with computer models and computer simulations. Will they agree? Can we improve the models that we've got through simple lab experiments and then try and compare them to bigger systems and real injection systems?
Now, you've got a video of this on the screen. It's rather beautiful. This flow, these fingers coming down.
The video was a model run by a computer to try and match some of the experiments that we do. And it shows a number, maybe 10 or more finger-sized masses of this carbon dioxide-rich water dropping down within the solution over time, and then fresh water rising up between these fingers to have more carbon dioxide dissolve in it. And over time, this consumes this free-phase CO2. It traps it in water, and that will slowly reduce the amount of buoyant CO2, ultimately reducing the potential for it to migrate. And this
migrate, I mean, you mean escape? So is it trapped there forever?
When it's dissolved in solution, it will react with the rocks and the minerals within the rocks and ultimately precipitate out as carbonate minerals such as calcite, the same minerals that form limestone, and then it'll lock it up for geological time periods. The CO2 will no longer move.
Chris, you've got to be pretty sure you've got this right, haven't you? If we're going to go down a road where we say carbon capture and storage is a solution for dealing with an excess of carbon dioxide, you've got to know that if you inject it, it's going to stay there.
Absolutely. It's got to be safe, and you've got to have confidence that it will stay underground, both for public acceptance and regulatory and carbon trading arrangements. But we can look at natural systems, where carbon dioxide formed through natural processes is stored in certain rocks for millions of years. And in the same way that oil and gas are trapped and you get oil and gas fields, you can get fields of natural carbon dioxide. And we can look at these and say, what's happened? What's the best bit about those natural fields that helps trap the carbon dioxide for long times? What can we learn from those? And can we pick the best sites to store it in the future?
Is there a danger this can be seen as an easy option to deal with carbon dioxide from, say, a power station?
It's not necessarily an easy option. It's technically feasible. There's a certain cost penalty to it. But at the moment, we vent the carbon dioxide to the atmosphere and appears to be leading to climate change. I mean, anything to reduce that's got to be good. Given the energy-producing technologies we have at the moment, we seem to have very little other option.
Chris Rochelle from the British Geological Survey, ending that report from Richard Hollingham. And pictures from the labs at Keyworth can be seen on our Facebook page, as can a few, in fact, of Perranporth Beach here in Cornwall. Well, that's the end of our podcast for today. Do check us out on that Facebook page and on Twitter. In our next podcast, a search for life in a lake in Antarctica. Until then, from the beach in North Cornwall, I'm Sue Nelson. Thanks for listening.